Okay, excellent. Welcome everyone to this IES webinar on Mocean Energy's approach to wave energy. We are delighted to be joined by Cameron McNatt, an experienced innovator in ocean energy. For the past 7 years as managing director, he and co-founder Chris Retzler have led Mocean Energy, developing novel wave energy technologies. He has a Master of Ocean Engineering from Oregon State University and a PhD from the University of Edinburgh. In this webinar, he's going to be talking about the work of Mocean Energy and developing technology that generates renewable energy from ocean waves. As usual, after the presentation, you will have the opportunity to ask questions, so please do submit these in the Q&A option at the bottom of your screen at any point during the presentation, and I will then read these out on your behalf later on. This webinar is being recorded and will be made available on the IES YouTube channel in due course. Thanks so much for logging in. It's great to see you all here, and I'll now hand over to you, Cameron. Thank you.
Great, thanks, Ethny. Hello, everybody. It's a pleasure to have the opportunity to speak with you this morning or afternoon. So I will be talking a bit about Mocean Energy, our approach to wave energy, which is quite generic. So I'll just give a bit of background on, Mocean Energy as a company, a little bit about our technology, what is our commercial approach, and then I'll talk more about the Blue X project, which was our project to build our first of a kind prototype wave energy converter. But first of all, what is wave energy? For those of you who don't know,
Waves form when wind blows over the ocean. Friction between the moving air and the surface of the water causes ripples that eventually grow to form waves. The size of waves depends largely on three things: the strength of the wind, and how long and far it blows unobstructed over a stretch of water. Which is why you find the biggest waves and the best surfing spots along the western coasts of North and South America, Europe, and parts of Africa and Australia. So with waves, it's not that each particle in the water travels from ocean to coast. Instead, each one remains almost in the same place, moving in a circle as it gets energized by the wind. The energy is then transferred along to the next particle and so on. They move with the most intensity at the surface, dwindling the deeper you go. Which kind of explains the sheer diversity of devices that attempt to capture different kinds of movement. At the surface, near the seafloor, and at the coast.
Okay, I'll just leave it there. I find that video better than I am at explaining what wave energy is. And it's quite a good video if anyone has the time. 11 minutes to watch it later on. So now for a bit of background on Mocean Energy. So Mocean was founded by myself and a guy called Chris Retzler in Edinburgh in 2015. I'm American. I came over to Edinburgh to do my PhD at the University of Edinburgh, working on, surprise, surprise, wave energy research. Chris was the principal scientist at a company called Polamis, which was once one of the biggest wave energy companies in the world, but unfortunately went into administration in 2014. And Chris and I met up through the university, started to work on some ideas, and eventually formed the company. We had some funding from a funding body called Wave Energy Scotland, and that was staged. So the project got larger, the funding got larger, and that allowed us to grow the team. In 2019, we were at 6 people. And then more recently, this is a picture taken in 2021 at the launch of our Blue X prototype. And now we've got 19 people. So it's been very exciting growth over the past few years. So a little bit about our technology. My background is in numerical modeling and software. I did numerical modeling of wave energy machines at the University of Edinburgh. And so when Chris and I started working together, we were looking at, can we use numerical models and optimization to find new shapes for wave energy converters? So we developed some code and use that to explore the design space, and found that yes, actually having different shapes for our wave energy devices does make a difference in terms of how much power they produce for a given size. And so we started out with fairly crude models, fairly sort of crude pictures, and then we built some physical models and tested them in wave tanks. But as we progressed through our technology development, those models became nicer and nicer, and so it just had a real opportunity to develop our technology. the majority of that technology development has come through what's called the Wave Energy Scotland Novel Wave Energy Converter Program, or WES NWEC program. And so that started at stage 0, essentially was just filling out an application for the program. That application, consisted in part of this numerical modeling exercise and optimization that we did, that we presented and said, here's our idea. This is what we'd like to do. We were successfully awarded a stage 1 project that we did in 2016. And I would describe that as kind of a feasibility study. We further developed the concept. We further optimized it. We estimated the levelized cost of energy. We did some engineering. We kind of expanded on it. Then we went through another stage gate. So 8 companies were awarded stage 1. They then down selected to 4 companies who were awarded a stage 2 project that went from 2017, 2018. We further refined our concept. We addressed some issues that we identified in stage 1, and we prepared for stage 3. They then down selected again and awarded 2 companies 3.3 million pounds to build a prototype of the design that was developed through this program. And I'll tell you more about that stage 3 at the end of this presentation. But that was a big launching point for us. Quite a big funding award, really enabled us to grow as a company. So what is Mocean's technology? Our technology is a hinged draft wave energy device with an innovative shape. So waves, I'll just play this video. So waves cause a reciprocating rotation about the hinge that drives a generator. We've developed new hull shapes through this optimization process that induce it to move more in waves. The more you move in waves, the more power you generate. So a little bit more about that optimization process. So it starts by writing code that programmatically creates lots of different shapes and then runs them through a simulation where the simulation estimates the energy production, things like that. We then wrap that geometry generation and simulation code up inside an optimization routine. So this is showing what's called a particle swarm optimization, where it's kind of like a flock of birds that fly around and looking for the optimal location. So the optimization changes all the parameters, trying to find the best one. And that returns a design, and we build that into small scale models and test them in wave tanks to validate that the result that we're getting is representative of reality. And so this process has resulted in what we call high performance wave energy machines. So the figure in the top right is showing our novel geometry compared to a standard hinge draft, where our novel geometry has the plates on the front and back, which we call wave channels, and the standard draft doesn't. On the x-axis, you have wavelength, and on the y-axis is power per mass. So we're producing a lot more power for the same size machine, which means that we can generate electricity at a lower cost of energy. So why is this machine behaving? What is it about these plates that induces it to produce more energy? I won't go into this in too much detail, except to say, well, what will I say? I'll say, so wave energy is essentially a mass spring system. So you have some mass of machine that's excited by an oscillatory wave system, and it bounces up and down in the sea. If you have just a single degree of freedom mass spring system, so just a mass on a spring, you can get there's one resonant frequency, one frequency at which it will bounce up and down. But what we have is a multi-degree of freedom system. So it only extracts power in the hinge, but it can move in surge, it can move in heave, it can move in pitch, as well as in the flex mode of motion. And what we found is that the coupling between these degrees of freedom, and this is a well understood physical principle, if you have multiple coupled degrees of freedom, you can have as many resonances as you have degrees of freedom. So in theory, we could have sort of 4 active resonances. And I think we do, in some analyses, but really what we find is that we have at least 2 resonant responses of the machine at 2 different wave periods, which amplifies the motion and broadens the bandwidth so that it responds over a variety of wave frequencies. Another really interesting result of the research we're doing is that the wave channels, this feature, this geometric feature that we have on the front of the machine, we believe creates a kind of fluid resonance. So we're working with a researcher, Cahal Cummings at Heriot-Watt University, to try to understand this better. And he believes it's a type of Helmholtz resonance. So I'll show a couple of videos here. This first one is from a numerical simulation. This is what the numerical model is predicting the fluid behavior will be like inside this sort of cup wave channel thing, and it's showing a resonant response of the fluid. So you're seeing that really high spike that goes way up and way down. That's clearly maybe not, that's not physically possible, but that's what the numerical model predicts. We've done some experiments to try to understand this. So this is sort of the experimental version of that video, and this is a wave channel shape in a flume. And if you look closely, you can see this kind of line moving past. That's the incident wave, which has a quite low wave amplitude. And then you can see the fluid moving inside the wave channel, which is moving with a much higher amplitude. So it's going up, and it's much higher than the incident wave, and it's sort of breaking a bit and sloshing. So we think these two aspects, the multiple resonances and the wave channel resonance, are keys to why geometrically we can get more power out of this machine than without our geometric features. And so what are we doing commercially as a company? Fine, you've got great technology, you got some funding to build a prototype. Obviously it's important for companies to generate some money. So our first market is to develop small, when I say small, it's all relatively small machines to provide power for offshore, off-grid equipment. So we're not, in the first market, we're not attempting to provide power to homes or to the mainland UK or Europe or anywhere, but we're building machines that are about the size of our prototype and using them to supply power for offshore projects. So these projects could be in the ocean science industry, they could be their applications in offshore wind. Maybe ironically, we're actually looking at applications in oil and gas. So this, the image on the right illustrates that type of application where we would provide power to an offshore tieback, which is what's connected to the seabed and tied back to a platform to extract hydrocarbons from the seabed. And so in this case, this is showing you the table is giving an example of how that project kind of commercially plays out. So with a traditional method of getting power to the tieback, which is using a cable. So traditionally they use a long subsea cable that connects the tieback to a platform for power. And so in the project we looked at, it was a 30-kilometer tieback, and it was going to cost about 13 million pounds to install that cable. For the customer, that's a big capital expense. It takes a long time to procure it. And the cable itself actually has a lot of embedded carbon and a large seabed footprint. It often has to be trenched and buried. So whereas we can provide power to this equipment for 7.5 million pounds, about 60% of the cost of the cable, we can do it on an OpEx basis. So we are, rather than selling the equipment to the customer, we own the wave energy device and we essentially sort of rent it to them. We can get that installed much more quickly, and it is clean, renewable energy, which is important in the oil and gas industry as they try to lower their carbon emissions. But I think also just to add that not all of these projects are about extraction of hydrocarbons. We're looking at CCS projects. So when you're putting CO2 into the seabed, you're using the same type of equipment, and they face very similar challenges in getting power to that equipment. So in support of our commercial rollout, we're doing a project called Renewables for Subsea Power, where we will deploy our existing prototype with an umbilical cable that takes the power down to the seabed, and it will be connected to some demonstration subsea equipment, including subsea batteries, an autonomous underwater vehicle, and what's called a subsea control system. We have funding to do this from the Net Zero Technology Center, as well as two customers, Harbor Energy and Serica Energy. So all being well, we'll have that equipment offshore this autumn and test through the winter and into the spring. But that is just the first step in our roadmap. So we are starting small with a product line we call Blue Star for offshore off-grid projects where they need tens of kilowatts of power. The next step in our roadmap is what we call the mid-scale, where we're developing a product line called Blue Horizon that will be rated in the hundreds of kilowatts. And we see, one of the markets that we're more excited about, or we think is quite a big market, is power for islands and remote communities. So we are engaging with stakeholders in different islands, and there is a gap where solar, some islands obviously are at northern latitudes, but solar, even in tropical islands, is not going to meet the entire needs of these islands. And currently islands are frequently running on diesel generators. The power it's obviously very CO2 intensive. The diesel has to be shipped in. It's getting very expensive. So as I say, solar isn't necessarily going to meet 100% of their clean energy requirements. Many islands don't want wind because of the visual impact, and many islands have great wave resources and are also, have a strong kind of historical and spiritual connection with the sea. So wave energy is really very much of interest, and because they already have high costs of energy, it's a good stepping stone market for this technology. But in the longer term, we think that the biggest opportunity is for wave energy at the grid scale, providing renewable power to mainland UK and mainland Europe and globally. And we see one model for its deployment is combined wind wave farms. So when you look at offshore wind farms, they have to space the turbines sort of 1 to 2 kilometers apart. And that's due to the aerodynamics of the wakes and spacing them apart so they don't interfere with one another. So essentially, these offshore wind farms have lots of space in between individual turbines that's not being used, but that has to be consented and has to be licensed. And they're already running cables out to these projects. And while, as we saw in that video at the beginning, waves are created by wind, there's typically a lag between, so you have a weather system that moves across the sea, across the ocean. It arrives at your wind farm and generates wind power. And then the waves that were created by that weather system arrive sometime after that. So you'll probably have some waves, of course, during the wind, but you get more waves after that. So because of that time lag, you're able to provide more power from your offshore farm. So we believe that combined wind wave farms will help to lower the overall cost of energy of these projects and provide more consistent and predictable power to the grid. So that's our commercial roadmap. Now I'll tell you a bit more about the BlueX project. So again, BlueX is our prototype wave energy device developed through the Wave Energy Scotland program that we completed and tested last year. So I'll start with a video, give myself a quick break from talking.
I'm Cameron McNatt. I'm the co-founder and managing director of Mocean Energy. I started Mocean Energy with Chris Retzler 5 years ago. We've developed this wave energy converter technology. It's a hinged raft, so 2 hulls connected by a hinge, and waves cause a rotation about the hulls that drives the generator. Compared to traditional hinged rafts, we're producing anywhere from 3 to 8 times as much power for the same size.
It's been years really in getting to this stage. It feels great to kind of finally get to a stage where it's so close.
The build phase of the device has taken about 2 years. Having such a fantastic team and a great group of contractors working for us has been an absolute pleasure, really. It's really made the project come together in a timely manner, and we're really excited about the next steps.
Hi, I'm Tim Hurst and I'm the Managing Director of Wave Energy Scotland. Scotland has a huge wave energy resource, probably the biggest in Europe, and that gives us the opportunity to use technology like this to generate low carbon electricity. So we're in Orkney, which is the home of the European Marine Energy Centre, a place where we're going to demonstrate the BlueX wave energy technology.
We built EMEC in Orkney because it's the best place to do it for learning how to make the most of wave energy. I've lost count how many machines we've had here. It's probably about a dozen or so wave energy machines, and a lot of lessons have been learned from this.
We're out at EMEC's Scapa Flow wave energy test site to see our wave energy converter BlueX. It's been going great so far. BlueX has been in the water for 2 months. Really great site to start our testing. We're getting about 1 weather system a month where we're generating some data. But we're also getting to prove a lot of our operations and verify the performance of the machine. So we're going to continue to test here in Scapa Flow through the autumn. We'll take the machine out and we'll add a bit of equipment on there. And next year we're doing a project called Renewables for Subsea Power, where we will connect BlueX to some subsea equipment and demonstrate providing power and communication to that equipment, which is the commercial use case.
The most thrilling bit has been seeing the machine in the water. We have dozens of sensors on board which are accumulating data, and we're examining that data, and we're working through and debugging the various issues that have arisen. It's been a phenomenal learning experience.
I think the most enjoyable part has been bringing the device to Orkney and getting it out into the water. Everything's really led up to that point. And actually being here, having the device working, gathering data has been really important and really exciting. Orkney is a fantastic place to test just because there's so much embedded knowledge and a really good supply chain up here. So it means we have really supportive contractors that have really enabled us to get the most out of testing the device.
Up here in Orkney, there's been a pretty small team, but we've got a great team with great facilities. Towards the end of this year, I hope we get a lot more waves at this site. We should, to winter, we'll get a lot more generating conditions and get export more power. And then, yeah, really looking forward to next year, moving to the east coast of Orkney and get out into more continuous generating conditions.
So the BlueX project, as I've said, was supported by Wave Energy Scotland. Wave Energy Scotland is a funding body funded through the Scottish government with a focus on wave energy. They've done a number of different programs, so not just ones focused on the wave energy devices per se, which is the one we were in, but they've done ones on the power takeoff, which is the generators, control systems, structures, and through these different programs, they've funded, as it says, 230 organizations and 96 projects with over 40 million pounds. It's been a really fantastic program that has really looked at this sort of complete aspect of the wave energy converter, and we're very fortunate to have been a part of it. So the BlueX project really started with a pretty rough design, to be honest. This is where we were at the end of stage 2. We had a sort of concept level design of how it would be built, but as these things go, it's the devil's in the details. There was so much more things that needed to be considered, everything from how it's towed to how people get on it and get in it to how cables are routed. All of that needed to be thought about and designed. And we were fortunate, very fortunate, to not have to do that all by ourselves, but we have numerous partners and subcontractors specializing in different aspects of the mechanical, electrical, control systems, generator, and so forth, who are helping us to get this machine designed. A big part of the development was the generator. So The generator is quite a specialized piece of equipment because we're doing, a back and forth motion, and it is high torque and low speed. That's not a very natural place for generators to operate. So we worked with the University of Edinburgh, who's developed a generator called the C-Gen that was pretty well suited for this application. That was built by a company called Fountain Design, and then a company called Supply Design provided the power electronics. Before we put the generator in the machine, we did what's called some back-to-back testing. So we actually built two of these drivetrains and connected them up to one another and used one to drive the other to ensure that the system was working before we integrated into the wave energy device. So once we had designed it and tested the generator, we started to build it. So the machine was fabricated at a relatively small fabricator in Cowdenbeath. We built it in sections and actually assembled the internals before it was completely welded together. Unfortunately, the fabricator wasn't big enough for us to build the entire machine in one piece inside their building. So, this is very much a lesson learned. We transported it in pieces from the fabricator out to the quayside in Rosyth here in Scotland to complete the build. But that was in January of 2021, which is not a very nice time to be doing this kind of work outside. I really feel for the team that were out there. And once again, not something that we could do by ourselves. We're really fortunate to be supported by a raft of partners and subcontractors. Once it had been built, so this photo was, I think, March 2021, there was still work to be done. So we did a process we would call wet commissioning. So we trialed lifting, we put it into the water for the first time. We had to get the ballast just right. So it was designed to sit level at a certain trim, but the as it's built, it's never quite exactly as you plan it. And so we used these water tanks and we filled them up with water to adjust the trim until we got the trim to where we wanted it. And then we replaced that water with steel ballast. Once it was complete, it was a pretty big thing, but it was small enough that it could be fit on a flatbed truck and actually road transported and then taken by ferry from Aberdeen up to Orkney. Once it was in Orkney, we got it in the water and we did some tow tests, and then we towed it out to the site where it was to be deployed. And there's a team in the bottom right corner looking very happy after the installation for the first time. So where was it tested? It was tested at what's called the European Marine Energy Center, which is a test center for wave and tidal devices that's actually been around since the early 2000s. We tested it in Scapa Flow, which is a relatively sheltered body of water where EMEC has a test site. It was a very good place to start our testing rather than going to more exposed Atlantic ocean conditions. So once we had it in the water, we were able to test it. This is a video of the machine under operation on a relatively wavy day. It's actually quite difficult to get this kind of drone footage because drone operators don't want to fly their drones when it's very windy, and you need a certain amount of wind to get waves at this site. But we did have built-in cameras. So this is showing on one of the wavier days out there from the mast, the camera that's on the comms mast. So it's also quite exciting to see. We had software that was monitoring the device. We had a sort of live data feed, but also the data was collected on the machine and then sent up to the cloud. And we also got a chance to practice our operations. So we went out and did some operations on the device while I was at sea. We also did one planned maintenance operation where we brought it back to the quayside, lifted it out, did some work, put it back in the water and towed it back out to site. And we were able to do that in 4 days, which we think was a real success for the project. And then at the end of the project, we, did some analysis. Well, I mean, at the end and kind of in parallel to it. So these are showing just a couple of graphs from that. So on the left-hand side is a towing plot, what is the force of the towing at different tow speeds. And on the right-hand side is a comparison of the measured electrical power produced for different sea states compared to what the numerical model predicted. And so what are some of the lessons learned from this project? It costs more than you think. It takes longer than you think. It's much more complicated than you think. But there's a lot of IP and know-how in building a prototype. So in the technology section of this, I talked about, we designed things on a computer and we tested them in a wave tank and we learned all this stuff about hydrodynamics. And yes, we did. That was great. That was really important to the technology development and the IP. But that's only a portion of what you need to know in order to actually build things that go out in the sea and do what you want them to do. So it was a really fantastic learning experience, and will serve us well moving forward into our commercial phase. But I think the most important lesson of all is, it takes a great team, and we're really fortunate at Mocean Energy to have such a good team, including Ethny's friend, Alfred, who's one of our numerical modelers, who introduced me to Ethny and got me the chance to speak to you all today. So thank you very much.
Thanks very much, Cameron. That was such an interesting presentation and great to hear about the kind of project from inception to where you've got to now and the future of what you're hoping to do with it. So thank you very much for that. And for the shout out to Toby and Alfred as well. That was nice. So all the attendees, please put your questions in the Q&A function at the bottom of your screen if you have any questions for Cameron. I just had a quick question first, which is to do with the placement of the device and kind of how you figure out the best place to put it, because obviously to limit impacts on marine life, but also when you talked about stage 2, which is thinking about delivering energy to island, I guess you have to think about the kind of tourist impacts it might have in tourism as well.
Sure. Yeah, I think when you're looking to do a project, especially a sort of wave farm type project, the site selection process is quite complicated. The whole, to be honest, it's not something we've really done yet. I mean, for our testing, we tested it at a sort of predefined test site. We did the testing we're doing this year. Actually, we did pick our own site, but you do have to consider the impacts. You have to consider the environmental impacts. You have to consider the impacts on marine transportation. Where do ships go? Where do fishermen go? You have to consider, are there any sort of marine archaeological sites out there? And so there are sort of methods, using GIS and consultation with stakeholders in that site selection process. So it is something that takes some time and some analysis and some human interactions. And I think to speak, I know I'm speaking to the Institution of Environmental Science today, and unfortunately I'm not an environmental scientist. I don't have a sort of full background in that, but I do know that the environmental consent, the environmental monitoring side for big projects is a really big aspect of it. And if you're doing a big wind farm, for example, they have to spend a couple years collecting data prior to that project going in. And then once that project has gone in, I'm sure there are probably people on this call that could tell us more about it.
Amazing. Thanks, Cameron. That was really useful. We got some questions coming through from attendees, so I'll get started on those. So you did test the device in Orkney, you mentioned, and we've asked, have you tested the device in conditions where there are a number of different wave conditions at the same time? For example, a long period swell running at a different direction to a short period storm swell. And additionally, how will tidal flow affect the prototype? Sure.
So the testing that we did last year was in Scapa flow, and it's a fairly limited fetch. So there was no swell. So it was purely just locally wind generated waves, which could be quite choppy. Where we're testing this year is going to be on the North Sea side of Orkney. So we will get a more variety. We'll get a a variety of conditions, probably some swell as well as some wind seas coming from different directions. Will also be exposed to more tidal conditions there. The sort of variety of conditions makes it very challenging to interpret the data and to compare the data to our numerical models. That's one thing that we found. So, prior to doing this testing, we were testing in wave tanks where you have, very good, almost perfect control over the conditions you're applying to your model. And so, you can say, oh, I applied this as an input and this is what I got as the output, and sort of try to match that to your numerical models and understand what happened. But you're really, when you're testing in a live sea environment, we have wave buoys. I think we'll have an ADCP for measuring currents at our site where we'll be testing this year, but there's still a lot of information that the wave buoy doesn't give you. It doesn't actually, it's not exactly at the same place where your wave energy device is. So it's really challenging to actually deal with all of this variety of environmental conditions that you're exposed to. So I'm not sure if that exactly answered the question, but.
Yeah, no, that was really useful. Thank you. We got another attendee saying this seems like a lot of work for a single generator unit. Do you have an estimate yet of the lifetime of a single unit, or how much maintenance a unit would require while in use?
Sure. So the products, we're called Blue Star, will have a 20-year lifespan, and we're looking to have 2 years between planned maintenance intervals. So it definitely was a lot of work, especially for the first of a kind. Well, it was a lot of work because it was the first of a kind. The second one won't be nearly as much work, and a lot of that work was design work and building things for the first time. So once you start to serialize that production, everything becomes much more efficient.
Great, thanks. And have you any prototypes or concepts in mind for future projects for harnessing tidal movements rather than just wind, i.e. wave?
No, we're not working in the tidal space.
Great. And are interactions with marine life, for example, marine mammals, monitored at test sites?
There was a group, I think, from Exeter University that was doing some environmental modeling. I don't think we were looking at marine mammals in our project. I mean, certainly the interactions that we saw the most were birds. So we did get a lot of birds landing on the device and pooping all over the device. But it is my understanding that from other projects that there really is minimal impact on the environment and marine mammals and other marine wildlife.
Okay, thank you. Well, it's been so interesting to hear about this project. I hope we can hear an update at some point about how the testing goes and the kind of first stages of the project, as you've talked about. So a massive thank you to you for coming and presenting on it today. It was really interesting. And thank you to all our attendees for coming today as well. And as I mentioned, it is being recorded and will be made available on our YouTube channel. Please do, if you're an IES member, please do log that you've watched this webinar on our IES CPD tool and take a look at our events page to see any upcoming events. A massive thank you to you, Cameron. It's been really great talking to you today.
Yeah, thanks very much for the opportunity. Bye, everybody.
Bye.